For thousands of years, we knew of only a handful of planets. The 5 wandering stars in our own night sky, and the Earth beneath our feet. From this tiny sample size, we built our idea of what a planet should be: a solid rocky world like Mars, or a majestic swirling gas giant like Jupiter. We thought we knew the rules. We thought we understood the limits of creation. We were wrong. In the last 3 decades, a revolution has swept through astronomy. We have discovered thousands of new worlds orbiting distant stars, a vast and diverse galactic family of exoplanets. And what they have shown us is that our solar system is not the template, it is just one quiet, orderly exception. The universe is a far stranger, more violent, and more imaginative place than we ever dreamed. Tonight, we journey to these new worlds. We will visit planets of burning ice, planets where it rains molten glass, and planets made of solid diamond. Prepare to have your definition of a planet shattered. Prepare to visit the strangest worlds we have ever discovered. We begin. For centuries, the existence of other worlds was a matter of pure philosophical speculation. But in the late 20th century, technology finally caught up with imagination. Astronomers had developed a new and incredibly precise technique to hunt for planets, a method that did not rely on seeing the planet itself. Instead, it relied on seeing the planet's invisible influence on its parent star. This is the radial velocity method, sometimes called the Doppler wobble. Imagine a parent and child holding hands and spinning around. The child is not the only one who moves. The parent also wobbles slightly as they are pulled by the child's smaller mass. A star and a planet are no different. As a planet orbits a star, its tiny gravitational pull causes the star to wobble back and forth, ever so slightly. We cannot see this wobble directly, but we can detect it in the star's light. As the star wobbles towards us, its light is compressed to slightly shorter, bluer wavelengths. As it wobbles away from us, its light is stretched to slightly longer, redder wavelengths. This is the Doppler effect. By measuring these tiny periodic shifts in a star's light, astronomers could infer the presence of an unseen planetary companion and even calculate its mass and its orbital period. In the early 1990s, 2 Swiss astronomers, Michel Mayor and Didier Queloz, were using this technique to survey stars in our galactic neighborhood. One of their targets was 51 Pegasi, a sun-like star about 50 light-years away in the constellation Pegasi. They expected that if they found a planet, it would be a gas giant like Jupiter, in a long, slow orbit that would take a decade or more to complete, just as our own theories of planet formation predicted. Gas giants, our models said, could only form in the cold outer regions of a solar system, far from their star. But this is not what they found. Their data showed a clear, strong, and impossibly fast wobble. The star was moving back and forth with a period of just 4.23 days. This meant that there was a massive planet orbiting the star, but it was orbiting so close that its year was only 4 days long. The planet had to be a gas giant, at least half the mass of Jupiter, but it was orbiting its star at a distance 8 times closer than Mercury orbits our own sun. This was scientific heresy. It was a planet that simply should not exist. A gas giant could not have formed that close to its star, where the heat and stellar wind would have blown away all the gas needed for its creation. The discovery was so strange that Mayor and Queloz spent months rechecking their data, convinced they had made a mistake, but the signal was undeniable. In October of 1995, they announced their discovery to a stunned and skeptical astronomical community. They had discovered a new class of planet, a celestial monster that would come to be known as a hot Jupiter. The implications were profound. If this planet existed, it meant that our neat, orderly theories of planet formation were at best incomplete. It meant that planets could be born in one part of a solar system and then migrate inward, a chaotic and violent process that would have completely reshaped their home system. The planet itself, which was given the designation 51 Pegasi b and later the name Dimidium, is a world of incredible extremes. It is a tidally locked gas giant, with one side perpetually facing its star. The dayside temperature is a scorching 1,000 degrees Celsius, or about 1,800 degrees Fahrenheit, hot enough to melt lead. Its atmosphere is likely being blasted away by its star's intense radiation, forming a long comet-like tail. It is a beautiful, violent, and utterly inhospitable world. The discovery of 51 Pegasi b opened the floodgates. Once astronomers knew what to look for, they began finding hot Jupiters everywhere. These strange, impossible planets turned out to be relatively common in the galaxy. The discovery, for which Mayor and Queloz would win the Nobel Prize in Physics in 2019, taught us the most important lesson in exoplanetary science. Expect to be surprised. The universe is not bound by our limited imagination. And 51 Pegasi b was just the first of a long line of strange, reality-defying worlds. From the impossible heat of the first hot Jupiter, our journey now takes us to a world that defies the very laws of common sense, a planet where the surface is a scorching furnace, yet it is believed to be made of a substance we associate with the deepest cold, ice. Welcome to Gliese 436b, a world that forces us to redefine what we mean by ice. It is a planet of burning solid water. Discovered in 2004, Gliese 436b orbits a small, cool red dwarf star about 33 light-years away. It is a Neptune-sized world, about 4 times the diameter of Earth and 22 times its mass. Pure like 51 Pegasi b, it is in an astonishingly close orbit, completing a full year in just 2.6 Earth days. Because of this proximity, its surface is blasted by its star's radiation, heating it to a temperature of about 440 degrees Celsius or over 800 degrees Fahrenheit. This is a temperature hot enough to melt zinc. When astronomers first calculated the planet's density, they were faced with a puzzle. The planet is far too dense to be a puffy gas giant like Jupiter, but it is not dense enough to be a rocky super-Earth. Its density is most consistent with a world composed primarily of water, and this is where the paradox begins. At 800 degrees Fahrenheit, water should exist as a superheated steam, a vapor. A planet made of water at this temperature should have an incredibly vast, puffy atmosphere. But Gliese 4336b is not puffy, it is compact. So how can a world be both incredibly hot and made of solid water? The answer lies in a force that is even more powerful than heat: pressure. The gravity of Gliese 436b is immense. This colossal gravitational pull crushes the water within the planet with a force of millions of Earth atmospheres. Under this kind of pressure, the rules of chemistry and physics begin to warp. Water molecules are not free to move around and turn into a gas, no matter how hot they get. Instead, they are squeezed together so tightly that they are forced to lock into a solid crystal lattice. This is not the familiar ice we find in our freezers, which is known as ice IH. This is a bizarre, exotic, high-pressure phase of water, a form of matter called hot ice. Scientists have created these forms of ice in laboratories, and they have names like Ice 7 and Ice 10. These are forms of water that remain solid at temperatures of hundreds or even thousands of degrees, as long as the pressure is high enough. So the leading model for Gliese 436b is a world with a small rocky core, surrounded by a massive mantle of this compressed, super hot solid ice. On top of this burning ice layer is a steamy atmosphere of water vapor. It is a true water world, but a water world from a nightmare, where the ocean is a solid block of burning crystal. But the strangeness of this planet does not end there. In 2015, astronomers using the Hubble Space Telescope made another astonishing discovery. Gliese 436b is surrounded by a colossal cloud of hydrogen, a cloud so vast it is 50 times the diameter of the parent star itself. The planet is evaporating. The intense radiation from the star is stripping the hydrogen from the water molecules in the planet's atmosphere in a process called photodissociation. This freed hydrogen then escapes the planet's gravity, forming a gigantic comet-like tail that trails behind the planet in its orbit. Gliese 436b is literally a giant evaporating comet, but one with a core of burning ice. It is losing its atmosphere at a rate of about 1,000 tons every second. While this sounds like a lot, the planet is so massive that it has likely lost only a tiny fraction of its total mass over its entire history. It is a world that perfectly encapsulates the beautiful and often paradoxical nature of the cosmos. It is a testament to the fact that in the universe, under the right conditions of temperature and pressure, even the most familiar substances can behave in ways that are profoundly and beautifully alien. Our next destination is one of the most visually striking and one of the most terrifying exoplanets ever discovered. It is a world of serene, beautiful, azure blue, a color that, from a distance, is hauntingly reminiscent of our own Earth. But make no mistake, this is no pale blue dot. This is a world of unimaginable violence, a place where the beautiful blue hue comes not from gentle oceans, but from a rain of molten glass, driven by winds faster than the speed of sound. This is HD 1109733b, located about 64 light-years away. HD 1189733b is another classic hot Jupiter, a gas giant orbiting its star in a blistering 2.2-day orbit. It is slightly larger and more massive than our own Jupiter, but its most famous feature is its color. In 2013, astronomers used the Hubble Space Telescope to measure the color of this planet directly. They did this by observing the system as the planet passed behind its star, by measuring the total light from the system when the planet was visible, and then subtracting the light of the star when the planet was hidden. They were able to isolate the light coming from the planet alone. The result was clear. The planet was a deep cobalt blue. But why is it blue? On Earth, the sky is blue because of a process called Rayleigh scattering, where the molecules in our atmosphere scatter blue light from the sun more effectively than red light. On HD 1189733b, the cause is thought to be far more exotic. The planet is tidally locked, with one side in perpetual day. The temperature on this day side is a scorching 1000 degrees Celsius. This is hot enough to vaporize not just water, but rock itself. The atmosphere of HD 1897733b is believed to be laced with tiny, glassy particles of silicate, the same material that makes up sand and glass on Earth. These microscopic silicate particles in the planet's upper atmosphere would scatter blue light, giving the planet its beautiful color. But this is not just a gentle, hazy blue. This is the sign of a truly hellish weather system. The extreme temperature difference between the planet's scorching day side and its slightly cooler night side creates a colossal pressure gradient that drives the most ferocious winds ever measured on an exoplanet. Astronomers have measured the speed of these winds by observing the Doppler shift of sodium atoms in the planet's atmosphere. The result is a wind speed of over 8,700 kilometers per hour, or about 5,400 miles per hour. That is more than 7 times the speed of sound. So what happens when you have an atmosphere filled with vaporized glass particles, and you subject it to winds that are 7 times the speed of sound? You get a rain of molten glass, blowing sideways. On the hot day side, the silicate vaporizes into the atmosphere. The ferocious winds then whip this vapor over to the slightly cooler night side. As the vapor cools, it condenses, not into gentle raindrops, but into tiny droplets of molten liquid glass. These glass raindrops are then blasted sideways by the supersonic winds, creating a perpetual planet-spanning storm of flying glass shards. To be in the atmosphere of HD 1809733b would be to be caught in a cosmic sandblaster, a hurricane of unimaginable proportions, where the rain is not water but molten glass moving at 5,400 miles per hour. It is a world that perfectly combines breathtaking beauty with apocalyptic violence. It is a powerful reminder that when we look out at the beautiful colors of the cosmos, we are often seeing the signs of physical processes so extreme and so alien that they defy our terrestrial experience. The beautiful blue of this planet is not the blue of life and water, but the blue of a beautiful, terrifying, glass-blown hell. From a world of glass rain, we now journey to a planet that may be the most valuable object in the entire known universe. A world that, due to a unique chemical quirk of its birth, may be composed not of the familiar water and rock of our own Earth, but of a substance we associate with incredible rarity and value. This is the super-Earth 55 Cancri A, the potential diamond planet. Located about 41 light-years away, 55 Cancri Podi orbits a bright sun-like star. It is a super-Earth, a rocky planet that is about twice the diameter and 8 times the mass of our own world. It is also in an incredibly tight orbit, whipping around its star in a mere 18 hours. This proximity makes its surface a scorching inferno, with a dayside temperature of about 2,400 degrees Celsius, or over 4,000 degrees Fahrenheit, hot enough to melt any known metal. But the temperature is not the strangest thing about this world. The real curiosity comes from the composition of its parent star, 55 Cancri A. Spectroscopic analysis has shown that this star is unusually rich in carbon. In fact, it has more carbon than oxygen. This is the reverse of our own sun, which is an oxygen-rich star. This chemical fingerprint is crucial because a star and its planets are all born from the same primordial disk of gas and dust. This means that 55 Cancri A is likely also a carbon-rich planet. This simple chemical difference has profound implications for the planet's geology. On a planet like Earth, where oxygen is more abundant than carbon, the planet's interior chemistry is dominated by silicates, compounds of silicon and oxygen, which make up the rock of our mantle and crust. But on a world where carbon is the dominant element, the interior chemistry would be completely different. The leading model for 55 Cancri E suggests a world of almost unimaginable wealth. Instead of a silicate mantle like Earth's, this planet could have a thick mantle made of solid diamond. Under the immense pressure of the planet's interior, the abundant carbon would be crushed into its most stable crystalline form. This would be a layer of pure solid diamond, thousands of kilometers thick, making up as much as a third of the planet's entire mass. Imagine the geology of such a world. Instead of volcanoes spewing molten silicate lava, 55 Cancri might have volcanoes that erupt liquid carbon, perhaps in the form of diamondoids or other exotic carbon compounds. Its surface, instead of being made of granite and basalt, might be a crust of graphite, the other, less glamorous form of pure carbon. The landscape could be a bizarre panorama of shimmering graphite plains and colossal jagged mountains of pure uncut diamond. The atmosphere would be just as alien. The intense heat would likely give it a thick, steamy atmosphere, but one rich in carbon compounds like carbon monoxide and methane, rather than the oxygen and nitrogen we are used to. It might even be possible for a kind of diamond liquid to exist at the surface, if the pressure and temperature are just right. Of course, the idea of a diamond planet is still a theory, a model based on the chemical data of its star. It is possible that the planet formed in a different part of its solar system and migrated inward, meaning its composition might not perfectly reflect its stars, but the possibility is a tantalizing one, and it is based on sound chemical principles. The discovery of 55 Cancri E and other potential carbon-rich worlds has opened up an entirely new branch of planetary science, forcing us to consider a whole new palette of geological and chemical possibilities. It teaches us that the very rock beneath our feet, the familiar silicates that make up our world, are not a universal constant. The universe is capable of building worlds from entirely different ingredients, creating geological wonders that would make the treasures of any king's treasury seem like worthless trinkets. Our journey has taken us to worlds of extreme heat and exotic composition. Now we venture to a world defined not by what it is, but by what it is not. A world of profound and unsettling darkness. This is the exoplanet TREPS-2b, a hot Jupiter with a reputation for being the darkest, most non-reflective planet ever discovered. It is a world that is literally blacker than coal. Located about 750 light-years away, TREPS-2b orbits a sun-like star. It is a classic hot Jupiter, a gas giant slightly larger than Jupiter, orbiting its star in a tight 2.5-day orbit. Like all such worlds, it is tidally locked, with one side perpetually facing its star. But when astronomers used the Kepler Space Telescope to measure the amount of light being reflected by this planet, they found something astonishing. TREPS-2b reflects less than 1% of the starlight that hits it. To put that into perspective, our own Jupiter, with its bright, colorful, and highly reflective ammonia clouds, reflects more than 30% of the sunlight that hits it. The Earth reflects a similar amount. Even the Moon, which we think of as a bright object in our night sky, reflects about 12% of sunlight. TREPS-2b is darker than any planet or moon in our solar system. It is darker than black acrylic paint, darker than fresh asphalt, darker than a lump of coal. It is a colossal planet-sized piece of absolute blackness. This discovery presents a profound mystery. Why is this planet so dark? On a gas giant, the reflectivity, or albedo, is determined by the composition of its clouds. Jupiter and Saturn are bright because they are covered in highly reflective clouds of ammonia ice crystals. The darkness of TREPS-2b must mean that it lacks these reflective clouds. But then, what is in its atmosphere that is so incredibly good at absorbing light? The answer remains one of the great puzzles of exoplanetary science. The leading theories suggest that the planet's incredibly hot atmosphere, over 1,000 degrees Celsius, is filled with light-absorbing chemicals. The atmosphere could be laced with a kind of gaseous titanium oxide, a chemical used in some sunscreens for its light-absorbing properties. Or it could be filled with vaporized sodium and potassium, elements that are known to be very effective at absorbing light in the visible spectrum. It's possible that the planet's intense heat prevents reflective clouds from forming in the upper atmosphere. The clouds might exist much deeper down, shrouded by a thick, high-altitude haze of these dark, light-absorbing chemicals. Whatever the cause, the planet is a cosmic stealth object, a true ghost in the starlight. But dark does not mean invisible. Because TREPS-2b is so incredibly hot, it emits its own light, just like a heated piece of metal. It glows, but it does not glow with a bright white light. It glows with a faint, deep, and menacing dull red light. If you could travel to this system and see the planet with your own eyes, it would be a terrifying and awe-inspiring sight. You would see a colossal, perfectly black sphere, silhouetted against the backdrop of the Milky Way. But as it orbited its star, you would see its day side, heated to 1,000 degrees, glowing with a faint, angry, cherry-red incandescence. It would be like looking at a hole in space, a hole that was faintly glowing from some internal, hellish fire. TREPS-2b is a world that challenges our most basic association of planets with reflected light. It is a reminder that some worlds do not shine by reflecting the light of their parent star, but instead absorb that light with an almost perfect efficiency, leaving only a faint, ghostly glow to betray their dark and mysterious nature. We have visited worlds that are impossibly hot, made of strange materials, and shrouded in darkness. Now we journey to a system that is home to a new class of planetary oddity, a type of world that seems to defy the very laws of gravity and density. These are the superpuff planets of the Kepler-51 system, worlds so light and so airy that they have been nicknamed puffball or cotton candy planets. They are planets that have the size of a giant, but the mass of a featherweight. Discovered by the Kepler Space Telescope, the Kepler-51 system, located about 2,600 light-years away, is home to 3 planets orbiting a young sun-like star. All 3 of these planets are bizarre. They are all roughly the size of Jupiter, which is about 11 times the diameter of Earth, but their masses are astonishingly low. The largest of them, Kepler-51b, is only about twice the mass of Earth. Another, Kepler-51d, is about 7 times the mass of Earth. Let's try to put this into perspective. These planets have a volume that is thousands of times larger than the Earth's, but a mass that is only a few times greater. This means their average density is incredibly, almost impossibly low. The density of Kepler-51b is calculated to be about 0.03 grams per cubic centimeter. For comparison, the density of water is 1 gram per cubic centimeter. The density of our own Saturn, the least dense planet in our solar system, is about 0.7 grams per cubic centimeter. It is famously less dense than water. The planets of the Kepler-51 system are over 20 times less dense than that. Their density is comparable to that of a styrofoam packing peanut or a ball of cotton candy. If you could place one of these planets in a bathtub large enough to hold it, it would float with ease. But what are these strange puffy worlds made of? How can a planet be so large and yet so light? This is a major ongoing mystery for planetary scientists. The leading theory is that these planets are not as large as they appear. They may have a much smaller solid core, which is surrounded by an incredibly vast, thick, and hazy atmosphere. The puffiness comes not from the planet's solid body, but from its enormous atmospheric envelope. The Kepler telescope detects planets by measuring the dip in starlight as they transit or pass in front of their star. A thick, hazy atmosphere could make the planet appear much larger and more opaque than its solid core actually is. It would be like trying to judge the size of a billiard ball that is hidden inside a giant, fluffy cloud of smoke. This atmosphere would likely be a thick, soupy mixture of hydrogen and helium, but it would also be filled with a significant haze of larger particles, perhaps photochemical smog or clouds of methane, that make it so opaque. The James Webb Space Telescope has studied the atmosphere of one of these planets, Kepler-51d, and its data seems to support this idea, showing a hazy, featureless atmosphere that is difficult to penetrate. Another possibility is that these planets are in a temporary transitional phase of their lives. The Kepler-51 system is very young, only about 500 million years old. It's possible that these planets are still glowing with the residual heat of their formation, which has puffed up their atmospheres to their current enormous size. Over the next few billion years, as they cool down and as their young star blasts them with radiation, they may lose a significant amount of this atmospheric envelope, shrinking down to become something more like a normal Neptune-sized planet. We may be catching them in a brief and spectacular puffy phase of their youth. Whatever the explanation, the superpuff planets of the Kepler-51 system have opened our eyes to a whole new category of world. They are a testament to the fact that the life story of a planet is complex and varied, and that worlds can go through strange and wonderful phases of evolution that we are only just beginning to discover and understand. For our entire history, humanity has known only one sun in the sky. The cycle of a single sunrise and a single sunset is the fundamental rhythm of our lives. But for most stars in the galaxy, this is not the case. The majority of stars are not solitary, like our sun. They are born in binary or multiple star systems, locked in a complex gravitational dance with one or more stellar companions. And any planets born in these systems will experience a sky that is profoundly, beautifully, and chaotically alien. To understand this, we journey to one of the most extreme examples ever found, the young gas giant HD 131399AB, a planet with 3 suns. Located about 340 light-years away in the constellation Centaurus, this remarkable system was discovered in 2016. The system is incredibly young, only about 16 million years old, a mere infant in cosmic terms. The planet itself, HD 131399AB, is a colossal gas giant, about 4 times the mass of our own Jupiter. But it is the star system it inhabits that makes it so extraordinary. The system is composed of 3 stars. The main star, HD 131399A, is a hot, bright, A-type star, more massive and luminous than our own sun. Orbiting this main star, at a great distance, is a pair of smaller, less massive stars, HD 131399b and HD 131399c. These two smaller stars are locked in a tight orbit around each other, forming a binary pair, and this binary pair, in turn, orbits the main star, A. It is a complex, hierarchical, triple star system. The giant planet AB is in a vast orbit around the main star, A. Its orbit is one of the widest ever discovered for a planet within a multiple star system, taking about 550 years to complete one full year. This wide orbit places it in a precarious gravitational position, where the pulls of all three stars are significant. Let's imagine what the sky would look like from the top of this planet's atmosphere, or from one of its hypothetical moons. The experience of a day would be unlike anything we can imagine. For about half of the planet's long, 550-year orbit, all three suns would be visible in the sky. The main star, A, would be the brightest and most dominant. The other two stars, B and C, would be much fainter, appearing as a close-set pair of brilliant star-like objects, but still far brighter than the full moon appears to us. During this long day season, which would last for over 200 Earth years, there would be no night. There would be a constant, triple sunlit daylight, with the three suns tracing complex, overlapping paths across the sky, casting multiple shadows of different colors. Then, as the planet continues in its orbit, the binary pair B and C would appear to draw closer and closer to the main star, A. Eventually, they would set just as the main star rises, or vice versa. This would lead to a period of more conventional, if brief, nights. The planet would experience a cycle of triple sunrises and triple sunsets, a spectacular and chaotic daily light show. But the most fascinating thing about this system is that, according to our models of orbital dynamics, it shouldn't be stable. The planet is in such a wide and eccentric orbit that the gravitational influence of the binary star pair should, eventually, disrupt its orbit and eject it from the system entirely. It is living on borrowed time. Because the system is so young, it's possible that we are seeing it in a brief, temporary configuration, a snapshot of a chaotic gravitational dance that will eventually end with the planet being flung out into the cold, dark emptiness of interstellar space. The discovery of HD 131399ab and other planets in multi-star systems, like the famous Tatooine planets that orbit two suns, has forced us to rethink the possibilities for planet formation. It shows us that planets can form even in the most chaotic and dynamically unstable environments. They are a testament to the resilience of the planet-forming process, and they offer us a tantalizing glimpse into what the sky might look like from the surface of a world that is not blessed with the simple, stable, and lonely sun that we call our own. Our journey through the gallery of strange worlds has shown us planets that are incredibly hot, incredibly dark, and incredibly young. Now we travel to the opposite extreme. We visit a world of unimaginable age, a planet so ancient that it is more than twice as old as our own Earth, a planet that was born when the universe itself was in its infancy. This is the exoplanet PSR B1620 et, unofficially nicknamed Methuselah. It is the oldest known planet in the universe. This ancient world resides in a truly exotic and spectacular location, at the heart of a dense globular cluster called Messier 4. Globular clusters are ancient, spherical swarms of hundreds of thousands of stars, all tightly bound by gravity. The stars within them are among the oldest in the galaxy, formed over 12 billion years ago, when the Milky Way itself was just beginning to take shape. The environment at the heart of a globular cluster is incredibly crowded and chaotic, a place where stars pass close to each other frequently. It is not the kind of place where you would expect to find a stable planetary system. And the star system that Methuselah orbits is stranger still. It is a binary system, but one composed of two stellar corpses. One star is a white dwarf, the dead, Earth-sized core of a sun-like star. The other is a pulsar. A pulsar is a rapidly spinning neutron star, the ultra-dense remnant of a massive star that exploded as a supernova. This particular pulsar spins about 100 times every second, sweeping a beam of radio waves across the cosmos like a celestial lighthouse. It was by timing the precise, clock-like pulses from this pulsar that astronomers were able to discover the planet. They noticed that the timing of the pulses was slightly off, arriving a little early, then a little late, in a regular periodic pattern. This indicated that the pulsar was wobbling back and forth, being tugged on by the gravity of not just its white dwarf companion, but also a third unseen object. That object was the planet, Methuselah. The planet itself is a gas giant, about 2.5 times the mass of Jupiter, and its age is estimated to be a staggering 12.7 billion years. To put this into perspective, our own solar system is only 4.5 billion years old. The universe itself is only 13.8 billion years old. This means that the Methuselah planet formed when the universe was only about 1 billion years old. This incredible age presents a profound cosmological puzzle. The early universe was made almost entirely of just hydrogen and helium, the two lightest elements forged in the Big Bang. The heavier elements that are needed to form planets like carbon, oxygen, and silicon, the elements astronomers call metals, were created later, in the hearts of the first generations of stars. The fact that a gas giant planet, which needs a solid core of rock and ice to form, could have come into existence so early in the universe's history challenges our theories of planet formation. It suggests that the first stars must have lived, died, and enriched the universe with heavy elements very, very quickly. The life story of this planet must have been one of incredible drama and violence. It likely did not form in its current orbit. The leading theory suggests that the planet originally formed in a normal solar system, orbiting a sun-like star. This solar system then drifted too close to the neutron star. In a complex gravitational dance called an exchange interaction, the planet's original star was kicked out, and the planet was captured into a new orbit around the neutron star. Later, the neutron star's gravity began to pull material from its new companion star, a process that spun the neutron star up to its current rapid rotation and turned the companion star into the white dwarf we see today. Methuselah is a survivor. It has lived through the death of its original star, a chaotic capture by a stellar corpse, and billions of years in the crowded, dangerous heart of a globular cluster. It is a true ancient, a relic from the dawn of cosmic time, a silent witness to almost the entire history of the universe. It is a powerful reminder that the story of planets is as old as the story of the stars themselves. Our cosmic tour has revealed that the universe is filled with planets born into extreme and violent circumstances. But sometimes, the greatest strangeness is not in a planet's birth, but in its death. Sometimes, the most bizarre story is not that of a survivor, but of a victim. We now turn our gaze to a class of stars that are not nurturing parents, but cosmic cannibals. Stars that have committed the ultimate celestial crime. They have consumed their own children. These are the planet-eater stars. We cannot witness such an event directly. The act of a star swallowing one of its own planets would be a relatively quiet and fleeting event on a galactic timescale. But the evidence of this crime can remain for billions of years, a chemical fingerprint left behind in the atmosphere of the star itself. To find this evidence, astronomers use one of the most powerful tools in their arsenal, spectroscopy. By passing a star's light through a prism, they can spread it out into a rainbow of its constituent colors, the spectrum, and embedded in the spectrum are dark lines like a celestial barcode. These absorption lines correspond to specific chemical elements in the star's atmosphere, each element absorbing light at its own unique set of wavelengths. A star's atmosphere is typically composed almost entirely of the lightest elements, hydrogen and helium. Heavier elements, the ones that make up rocky planets, like iron, silicon, magnesium, and aluminum, are present, but usually only in trace amounts. Crucially, in a normal, well-behaved star, these heavy elements are mixed evenly within its outer layers. But in the last decade, we have begun to find stars that are different, stars with a bizarre and unnatural chemical imbalance. One of the most famous and unsettling examples is the star HD 2404330, unofficially nicknamed Kronos, after the Titan from Greek mythology who devoured his own children. Kronos is a sun-like star, part of a binary pair with another star named Krios. The two stars were almost certainly born from the same cloud of gas and dust, so they should have a nearly identical chemical composition, but they do not. Spectroscopic analysis revealed that Kronos has a dramatically different chemical fingerprint than its companion. It is unusually rich in what are known as refractory elements, the heavy rocky materials that have a high condensation temperature, the very stuff that planets are made of. At the same time, it is not enriched in volatile elements, the lighter gassy materials that make up the bulk of a star's atmosphere. This specific, peculiar pattern of chemical enrichment is the smoking gun. The evidence points to a grim conclusion. At some point in its history, Kronos consumed one or more of its own rocky planets. The star did not just accrete random gas and dust, it ingested fully formed planets. The amount of extra rocky material in Kronos' atmosphere is equivalent to about 15 Earth masses. It is as if the star swallowed a super-Earth, or a collection of smaller rocky worlds. The planets would have been pulled from their stable orbits, perhaps by the gravitational influence of a larger planet in the system, and sent on a long, plunging death spiral into their own sun. As the planet fell into the star, Its rocky material would have been vaporized and mixed into the star's convective outer layer, polluting its atmosphere with this telltale excess of heavy elements. Its companion star, Krios, orbiting at a great distance, was too far away to share in the feast, and so its atmosphere remains pristine and unpolluted, a perfect control group for the experiment. The Kronos system is not unique. As our spectroscopic surveys have become more precise, we are finding more and more of these chemically peculiar stars. They are a stark reminder that planetary systems are not always the calm, stable, clockwork places we see in our own solar system. They can be violent, chaotic, and dynamically unstable places where a planet's existence can be brutally cut short. The strangest feature of these systems is not a planet we can see, but the ghostly, chemical echo of a planet that is no longer there, its life and substance now just a faint, anomalous line in the light of its parent star. For our entire journey, we have operated under a fundamental assumption that a planet is a world that orbits a star. The star is the anchor, the source of light and heat, the center of the system. But what if this assumption is wrong? What if the most common type of planet in the universe is one that has no star at all? We now venture into the deepest, darkest, and loneliest realm of the planetary kingdom, the realm of the rogue planets. These are the ultimate orphans of the cosmos. They are worlds that were born in a planetary system, just like our Earth, but were violently ejected into the unending darkness of interstellar space. As we have learned, the early life of a solar system is a chaotic and violent game of gravitational billiards. In this game, a close encounter with a massive gas giant can act like a colossal slingshot, accelerating a smaller planet with such force that it achieves escape velocity and is flung out of the system forever. For a long time, these rogue planets were purely theoretical objects. Finding a planet-sized object that emits no light of its own, lost in the vast dark ocean between the stars, seemed like an impossible task. It would be like trying to find a single black bowling ball in the middle of the Pacific Ocean at night. But astronomers devised an ingenious method to hunt for these ghosts, a method that uses gravity itself as a lens. This is the technique of gravitational microlensing. As predicted by Einstein, massive objects warp the fabric of space-time. When a rogue planet by pure chance passes almost perfectly in front of a distant, unrelated star, its gravity can bend and magnify the light of that background star. For a brief period, from a few hours to a few days, the background star will appear to get brighter and then fade back to normal in a very specific, predictable way. By monitoring hundreds of millions of stars in the most crowded parts of our galaxy, surveys are constantly searching for these telltale brightening events. A brief flicker could be the signature of an Earth mass rogue. A longer, more pronounced brightening could be a wandering Jupiter. And we have found them. Dozens of candidate rogue planets have been discovered using this method, confirming that this vast hidden population is real. The statistical analysis from these surveys is staggering. The current estimates suggest that there could be more rogue planets in the Milky Way than there are stars. For every point of light you see in the night sky, there could be 100 cold, dark, and lonely worlds drifting silently and invisibly through the void. These orphans, not the starbound planets like ours, may be the true galactic standard. What would life be like on such a world? Its surface would be a realm of absolute cold, a frozen hellscape at a temperature of near absolute zero. But the story might be different in its interior. A large rocky rogue planet, a super-Earth, would have been born with a significant amount of radioactive elements in its core. The slow decay of these elements would generate a steady internal heat, a process of natural nuclear fission. This internal furnace, insulated by a thick crust of rock and a colossal ice shell, could be powerful enough to maintain an ocean of liquid water deep beneath the surface. This would be a global, subsurface ocean, a world of water in total and absolute darkness. Life here would not be powered by a sun, but by the planet's own geothermal heat, likely centered around hydrothermal vents on the ocean floor. It would be a biosphere completely divorced from the light, a self-contained ecosystem powered by chemosynthesis. It is a tantalizing and scientifically plausible idea. The most common habitats for life in the universe may not be the warm, sunlit surfaces of Earth-like planets, but the dark, hidden oceans of these countless cosmic orphans. They are the ultimate strange worlds, their very existence challenging our most basic idea that a planet needs a sun to be a home. Our grand tour of the cosmic zoo is drawing to a close. We have visited a gallery of worlds that are stranger than any science fiction writer could have imagined. But our journey so far has been, in many ways, an indirect one. We have learned about these planets by observing their gravitational pull on their stars, or by analyzing the faint starlight that has passed through their atmospheres. We have inferred their properties through clever and painstaking detective work. The next great frontier in the exploration of strange worlds is to move from these indirect methods to the ultimate prize, direct imaging. The goal is to take an actual photograph of an exoplanet, to see it as a distinct point of light, a pale blue dot orbiting another sun. The challenge of direct imaging is almost impossible to overstate. A planet does not produce its own light. It only reflects the light of its parent star, and a star is about 1 billion times brighter than a rocky planet orbiting it. Trying to see an Earth-like planet next to a sun-like star is like trying to spot a firefly sitting on the edge of a colossal blazing searchlight from 1,000 miles away. The star's glare completely overwhelms the faint light of the planet. To overcome this, astronomers have developed two ingenious techniques. The first is the coronagraph. A coronagraph is an instrument that uses a small, precisely shaped mask to block out the direct light of the star, creating an artificial eclipse. This allows the much fainter light of any orbiting planets to become visible. The second technique is called a star shade. This would be a separate spacecraft, shaped like a giant, multi-petaled flower that would fly tens of thousands of kilometers in front of a space telescope. It would be positioned with millimeter precision to cast a perfect dark shadow of the star onto the telescope, allowing the telescope to see the faint planets in its orbit. These technologies are no longer theoretical. The James Webb Space Telescope is equipped with a suite of advanced coronagraphs, and it has already begun to take direct images of a handful of young, massive, gas giant exoplanets that are far from their stars and still glowing with the heat of their own formation. These are the first, tentative steps into this new era, but the ultimate goal is to directly image a small, rocky, Earth-like planet. This will require a new generation of even more powerful space telescopes. Concepts are now on the drawing board for a habitable worlds observatory, a large direct imaging space telescope that could launch in the late 2030s or early 2040s. Such a telescope, equipped with an advanced coronagraph or a star shade, could be the first instrument in human history to take a direct photograph of another Earth. And it wouldn't just be a picture. By passing that faint pinpoint of planetary light through a spectrograph, we could analyze its chemical composition. We could search its atmosphere for the telltale biosignatures of life, the chemical fingerprints of oxygen, methane, and water vapor. This is the ultimate goal of exoplanet science. It is the search for a definitive answer to the question, are we alone? The next few decades will be a golden age of discovery. The James Webb Space Telescope will continue to analyze the atmospheres of transiting worlds. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct a massive microlensing survey that could discover thousands of new rogue planets. And on the horizon are the great direct imaging observatories that will finally give us a picture of a world like our own. The strangest planets we have ever discovered are likely just the tip of the cosmic iceberg, the first, most obvious oddities in a universe that is teeming with a diversity of worlds that we are only just beginning to comprehend. We began our journey with the simple idea that our solar system was the blueprint for the cosmos. We have returned with that idea completely and beautifully shattered. Our tour of the strangest planets we have ever discovered has been a lesson in cosmic humility and a celebration of the universe's boundless imagination. We have seen that the neat, orderly architecture of our own solar system is not the rule, but a quiet exception. The galaxy is filled with hot Jupiters and scorching 4-day orbits, worlds that have migrated through their systems in a chaotic wrecking ball dance. We have journeyed to a planet of burning solid ice and a world where the sky rains molten glass, driven by supersonic winds. We have stood on the shores of a theoretical diamond world and stared into the profound, light-absorbing blackness of a planet darker than coal. We have marveled at the impossible physics of puffball planets, worlds with the density of cotton candy. We have gazed at the chaotic, triple sunlit sky of a world whose very existence is a temporary gravitational miracle. We have touched a planet so ancient it is a relic from the dawn of time, and we have seen the ghostly chemical evidence of worlds that have been devoured by their own parent stars. We have learned that the most common planets of all may be the lonely orphans, the sunless worlds that wander the interstellar dark. Each of these strange worlds is more than just a cosmic curiosity. Each one is a new data point, a new piece of the puzzle that is forcing us to rewrite our theories of how planets are born and how they evolve. They are showing us that the universe is a far more diverse, dynamic, and creative place than we ever thought possible. The rules we thought were universal are merely local bylaws. We are living in a unique and privileged moment in the history of human exploration. We are the first generation to know, for a fact, that planets are everywhere. We are the first generation to begin to glimpse their incredible diversity. We are the cartographers of new worlds, the explorers of a vast, unseen cosmos. The strangest planets we have discovered so far have taught us one simple, profound lesson. The universe has a better imagination than we do. And the most exciting part is knowing that the most bizarre, the most beautiful, and the most world-changing discoveries are still out there, waiting in the faint, flickering light of a distant star. The journey has just begun.